Okay, so welcome everybody and good afternoon. My name is José Fonseca. I work at Mesa de la Simulación in CEA exactly, and I work with the library Parflow on AMR aspects. So just to start with a little introduction for those external to the project or to the EoCoE consortium. Why we do this? Well, we start with the notion that accurate simulation of variable saturated flow in porous media is really important in many problems, and the common approach is to complete a numerical solution of the Richards equation, which I put here as a reference. Here, well, of course, you solve for the pressure P, and here you have other variables like the porosity or the saturation of the fluid, but I'm not going into detail there for that. Why it's challenging to solve this equation is because it is nonlinear, and this factor here, which is the conductivity tensor, can introduce really large variations in the coefficients. So another reason is that the requirement of really high resolution in spatial and temporal discretizations, and this goes to the consequence that high performance computing is necessary to tackle this problem. So what is exactly Parflow? So as you saw a couple of presentations ago, it's an integrated parallel watershed model which simulates subsurface and surface flow. It actually then provides a solver for the Richards equation based on a cell-centered finite difference discretization. So really big code, more than 100,000 lines. Actually, Jaro gave a more accurate number, 150. It's built using distributed parallelism, and as you saw in the presentation from Jaro, this newest version, it also has support for accelerators. But the work that I'm presenting here is completely orthogonal from that. So I'm focused in the version which is only using MPI. So how this code parallelize the problem? Well, it does it by parallelizing the mesh as many PDE-based solvers. It takes the computational grid and it's split in non-overlapping blocks, which are called subgrids. And each subgrid is assigned to a unique process in the parallel machine. These subgrids and processes are logically arranged in lexicographical ordering. And all of this is taking place internally in Parflow. And in a previous work, we delegate this whole process or the mesh management to another library, which I will introduce in the next slide, but which basically we use a tree structure and put on each of the leaves of the tree structure one of these subgrids to translate it into an equivalent Parflow grid. And right now, what my position right now has to do is to use this tree structure, which immediately leads to the idea of adaptive mesh refinement or local grid refinement, to introduce this feature into Parflow. The library we use to do that is called pforest, which is a library based on this idea that a refinement scheme or a mesh can be encoded using a tree structure, and a space filling cube running over the leaves of that tree defines a total ordering of the elements of the mesh, as you see to the right. So what pforest does is it exploits the properties of a particular SFC, the space filling curve, to implement or to give the user a set of algorithms for sorting, searching, to implement mesh partition and a mesh adaptation. The library is also well known for good parallel scalability and using as a based mesh oracle in many other libraries and well known like deal 2, for example. Now let's go back and take a closer look into Parflow, and in two key points in particular. The first one would be that how Parflow computes the MPI envelope. What that means, how the information defined and how the communication between MPI ranks has to take place. Essentially, in Parflow, you can think, or conceptually, in Parflow, subgrids are basically in sets of integers, which correspond to the indexes of the degrees of freedom. And you perform, or Parflow performs, stencil calculations on those indices to decide how the envelope is. So for instance, if you have here a subgrid, which I'll call in a two-dimensional situation, I call this subgrid C0 to S3. If the stencil is such that you need information from the adjacent neighbor, then what Parflow will do is that it will operate on the crosses here in each corner, which will be the numbering of the nodes, and will actually do set operations. For instance, taking this S0 and shifting to the right, and to see which points into S1 have intersection with S0, and if we use that information to define what should be put in the MPI envelope, or what have to be put into the sends and the MPI receives. I emphasize here the dots here in the middle that are here to emphasize that this is a cell-centered discretization, and of course the physical location of a point is obtained by a simple transformation of the index. A second, of course, I'm putting this here because now that in my implementation, I am changing quite a lot these index sets. So this whole operation, or this whole machinery of doing sets operations, just intersecting sets, which it might not work, or may give empty sets, or in some cases. But we go to that in a moment. The second point where you have to, or I had to take a closer look, is that Parflow has its own octree structure internally, which is used to depict or to loop efficiently among, let's say, subdomains having different physical properties. And the octree, which is implemented inside of Parflow, is just a classical one, in which if you want to represent a domain, like in this picture here, with this block here, you take a big box and surround it, and then you start refining this box until all the sub boxes are completely contained in the object that you want to represent. And as I said before, this is heavily used inside Parflow to implement loops over a particular physical region. So we need to find out the relation between this octree and now our octree that I'm putting in by using this adaptive library before us in. So concerning the MPI envelope, we have generalized the previous approach in order that it honors the following communication pattern. Whenever I have the situation that I create a coarse subgrid is neighboring two finer subgrids, then I artificially or create these children of the bigger one in order then to host the possible messages that the children might send to the first one. I mean, if we leave this unchanged, then I run in the situation in these two guys here, this top and bottom will send two messages here, and there is no space actually to copy the message, or the code won't be able to see that it has to send a message there. And in the other way around, when the big one has to send to the smaller ones, then I just send the same information to both of them. So I send 2 times the same message. So the previous this set based on intersections approach to compute send and receive regions and the MPI envelope has been generalized to account or to give this kind of situation. So as an example, imagine that you have this subgrid here, this big one, and you as well you're in the situation if you have adjacent neighbor information needs. So what Parflow will do is to take this one, the big one, and shift it what the stencil says to the right, and then compute the intersection. Here it won't be good defined, or it will be a wrong result. So what we do is to create a parent of the smaller grid here. Forget for a moment about the smaller ones and execute the normal code, Parflow code, which will see this intersection correctly here, and then just map it back to the smaller one. Of course, it's more complicated than that. In the actual code, you have to account for other cases, but this is just to illustrate a way in which this is done. Concerning this Parflow's own octree, I think you saw these kind of loops also in Jaro's presentation. Parflow actually had before a view in using local grid refinement. So in the subgrids, actually there is a parameter which defines a refinement, but it was never used. And in the practice, in all these loops that appear everywhere in the code, this R here representing that level is actually 0. So what we did is we dive into how this octree inside Parflow is defined, and which we kind of find out what is the relationship with the octree we are creating with pForest, and relate these 2 levels, and put here the right number in such a way that these loops actually run over the correct points when we activate the local grid refinement. So saying that, then we are ready to talk about the actual discretization. And the key observation that we are following is a result from these persons here, which I put the citation. It's like if you are in a situation like in the picture, and if you want to compute the Laplacian, say at the point p hat, then you could of course, if you want to do that, you in a classical finite difference approach, you would like to use P2 and P0. No, sorry, I'm saying this wrong. I want to compute the Laplacian at P3. So the available points are P5, P4, and you would like to use P hat and P tilde, but you don't have them, so you interpolate them from the points you have. If you follow this approach and then do a standard failure analysis, you discover that these 2 terms here approximate the following operators. ILX approximates something that looks like the Laplacian, or the second derivative of P in X. There's some noise, and the same applies for the other term. Of course, if we are in a uniform situation, this term, this PYY 1/5 over 5, will disappear, and as well this here. So the key observation done in this paper is that you can wait out these 2 in order to actually obtain PXX and PYY and still have the desired accuracy. So the whole the whole work done before into ensuring that the right MPI envelope is computed and ensuring that that these two octree structures are compatible is it was done in order to be able to use this approach in Parflow. So in order to do that, then you have to make sure, or it's not necessary, but it makes the life easier. We only use 2-to-1 phase balance trees in order to have only this situation, that the size of the difference between two phases is almost a factor of 2. We assume that the subgrids have an even number of points in each coordinate direction. And some technical issues inside Parflow. There are some 2D projected grids from the 3D one, which in 3D, in case of an adaptive mesh, the projection does not make sense. So we just have to use 3D ones. And of course, we have to now generalize the approach before to a 3D case, and for the case of our equation, which is Richard's equation. So we have to list and treat all the relevant cases. Of course, I started treating the Richard's equation with constant coefficients or everything like easy, such it reduces and as a first step to a Poisson equation. So, for example, one of the many cases that may arise under these restrictions is in 3D, if you have 5 phases of the same size in one phase, which is finer. So in that, let's say that this is at the plus X direction. So at that phase, you have 4 neighbors. So if you you combine information of these 4 neighbors to compute the point that you will need to do the right difference and do the corresponding Taylor analysis, you will discover then that the standard or this final difference approximation will approximate an operator which has this form. And you see these factors here appearing again. Since in the other phases you have the same size neighbors, then the final difference approximation yields what you expect. And applying the idea from before, then you just need to weight appropriately these 3 terms in order to obtain an approximation of the Laplacian. This can be generalized also to non-constant coefficients and doing pretty much the same analysis. By doing that, I am already in a position to solve things, simpler things with Parflow using an statically refined mesh. And it means I'm just refining at the beginning and leaving the mesh the whole time like that. And so to the left is just a solution, a manufactured solution of the Richard's equation. And to the right, I'm just picturing the same with a mesh I just randomly refine up to 2 levels of refinement. Well, this is just to illustrate that the approach is reproducing something that which looks meaningful. Unfortunately, I don't have yet, or I'm not yet in a position to do a meaningful example with this, because I'm coming to that. I'm still doing finding quite some bugs on my own implementation, but maybe the main reason I cannot do something like more scaling or a bigger problem is that we have not yet a preconditioner that works in the case of when the grid is locally refined. This is something I am currently investigating, and by doing all this debugging and testing, I just noticed as well that I found room for several optimizations. For instance, these inner go cells that I talked at the beginning. There are some cases I'm allocating too many of them and wasting some resources, and as well, handle more general coefficients, because for the example I showed before, basically the conductivity tensor is constant or its identity, so it's easier. Yes, this will be what I wanted to share with you. I'm really happy to take questions.
Thank you very much, Jose. If there are any questions.
Oh, I stopped sharing, sorry.
Yes, Ulrich, I see that your hand is raised.
So thanks for the presentation. My question would be, what would be the expected difficulties for the preconditioners that you envision with pForest? You know, I'm kind of thinking of something like ILU-based preconditioners or something that needs a more complicated communication structure, maybe. I don't know, but do you have anything special in mind?
Oh, okay. I'm not really okay. That there is in Parflow uses internally high preconditioners, and two of the essentially there are three of them, and two of them are not well suited to this kind of refinement because they are more in the direction of patch space refinement. I know the Boomer AMG works well with AMR because I have used it before, but in other kind of discretizations, like more finite element ones. So I will probably well, my first guess is that the smoother operation is not well defined in the adaptive case. So it might be necessary to hard code or to ask or to develop a self how to say, to develop a self AMG kind of preconditioner and just pop the information from the communication provided by pForest, which as well I have. There are some experience with that, but I'm not so sure if this is the right approach.
Okay, thank you very much.
Thank you.